All right, so now we're going to do a very, very long problem. But just before we do that, just review. So this is the impulse momentum principle. We usually, I mean, look at all the different parts to it, right? So people say, well, what is it? It's the whole thing. It really is. So the definition of impulse is this integral, and this is also equal to that, and that's equal to that, which equals that, which equals that. I mean, you know, that's the whole thing. And again, you have to know that momentum is mass times velocity. So there's a lot to it. Okay, so here's an incredibly long problem. A 200-gram rubber ball is released from rest at a height of 2 meters, falls to the floor, bounces, rebounds. The force of the floor on the ball, so that's normal force, right, is shown below. You can see it's certainly not constant, right? I mean, you know, 0, then woo. Okay, all right. How high does the ball rebound? Okay, so let's do it. Okay, so how high does the ball rebound? That sounds like kinematics, right? So we got to draw the complete pictorial representation. Now you might say, wait a second, how can you use kinematics? You just told me that we can't use kinematics. Well, we can use kinematics for part of the problem, but we'll have to use impulse momentum for the other part that we can't use kinematics. Okay? All right, so first of all, we're holding a ball. We drop it, it bounces, it rebounds. We want to know how high it is. How many points, and this is the normal force, how many points do we need in our pictorial representation? So think about that for a minute. How many points? Four. A starting point, and then we need before the collision, immediately before the collision, immediately after collision, and then when it bounces up. So 4 points. So you can see it's going to be complicated, right? All right, so I think I have it drawn. Okay. Okay, and you know, this is just a y problem, right? So we don't need any x's. We don't have any time information at all, correct? No time information. So forget about it, right? So here, so y0, v0y. Okay, the a is this way, right? Just, you know, gravity. y1, v1y, that's right before the collision. This is right after the collision. y2, v2y, and then this is y3, v3y. Okay, so let's see, what did I call this the origin. Kind of makes sense, right? The floor, you know. So this is 2 meters. This is 0. We're dropping it from rest. Okay, this is 0, right? y1 is 0. We don't know what the velocity is right before the collision, but we can find out from kinematics. Okay, y2 is 0, v2y. This is after the collision, so we're going to have to use impulse momentum here, you know. And then v3y is where it stops, and y3 is what we want. And a equals minus g. Okay. All right. Velocity right before the collision, velocity right after the collision. Okay, so this is what we want. All right, so how are we going to get it? How are we going to get it? Well, how do we get a height? Just use kinematics, right? Just use kinematics. Okay, but in order to get this, you know, what do we need? Well, you know, v final squared equals v initial squared plus 2a delta y. Well, we know this velocity, so we're going to need this velocity, right? We're going to need the velocity right after the collision. Uh-oh! And I just told you a minute ago, right? How are we going to get that? We can't use kinematics because we have this time-varying force, you know, the normal force. So we have to get that from impulse momentum. Okay, whatever, we'll do it. Now, in order to use impulse momentum to find this, what else we got to know? Well, we got to know the impulse, right? We got to know the impulse, and we got to know this. Oh golly, right? So we got to know the impulse, and we have to know v1y. Well, let's talk about the impulse. How many impulses are there? Well, there's gravity, and there's a normal force. So there's 2 impulses. Man, this is getting complicated. All right, so there's 2 impulses, okay? All right, so we have to do that. All right, but then we also have to figure this out. How do we do that? Well, that's just kinematics, right? Okay, so you can see there's a lot of work involved, all right? Okay, so we have to kind of work backwards, you know? So first we'll calculate V1y just with kinematics. Then we have to calculate impulse and impulses, and then since we know this and the impulses, we know that. Then if we know that, we can get that. So wow, a lot of work. All right, let's just do it. Okay, so the first thing we want to do is just V1y. Okay, so V1y. All right, so that's just good old kinematics. We can handle it. So V1y squared equals V0y squared minus 2g delta y, correct? Now, let's be a little careful. I don't want to just say delta y. I want to say, because we're just looking at this here, right? So rather than saying delta y, I'm going to say y final minus y initial. So y1 minus y0. y1 minus y0. Then we won't get mixed up, all right? Okay, so we just want v1y, so we just take the square root. Right. Okay, so v0 is 0, so we get 0 minus 2, 9.8 meters per second squared. Okay, y1 is 0, so we get 0 minus 2 meters. And we have a minus sign there and a minus sign there, so we're not going to get in any trouble. But hold it. We know it's going down, so when we take the square root, we better put a minus sign, huh? So we get minus 6.26 meters per second. Okay, so that's just v1y. You know, we could have done that a month ago, right? Just using kinematics. Now we want to figure out v2y. Oh, golly. So that's going to, all right, so now v2y. And that's after the collision, right? And so that's impulse momentum. We can do it. Okay, so J is the impulse. That's equal to delta P. That's mv2 minus mv1, right? It's just during the collision, okay? So v2y, v1y. I just put, I guess I should be good, right? Oh, whatever. Okay, all right? Now, we just want v2y, so just put that on the other side. So therefore, v2y equals j plus mv1y divided by m. Okay, which is the same thing as j over m plus v1y. Okay, all right, so now we know how to get v2y. And like we said earlier, you know, in order to do that, we need to know the j, the total impulse. No problem. All right, so, but again, you know, there's two impulses, right? There's the normal force impulse, and there's the gravitational force impulse. Let's do this one first. All right, so let's see. So remember, this is the total, right? This j is the total impulse. Okay, so we have two. So we have j floor, or I should have said j normal, who cares? All right, so it's just the area under the curve, big deal, I can do that. It's half a base times height, right? Half base times height of a triangle. So half, okay, what's the base? 10 milliseconds. So 10 times 10 minus 3 seconds, right? 10 milliseconds. And the height is 480 newtons. 480 newtons. And that comes out to be 2.4 newton seconds. Okay, that's J floor. All right. Now, what's the impulse for gravity? I don't know. I mean, they didn't give us the graph. How are we supposed to know? Well, yeah, we do know, okay? We can handle it, all right? But what we have to do, though, we have to draw our own force versus time graph, okay? All right, we got to do that ourselves. Okay, we can do it. Come on. What's so great about the force of gravity? It's constant, right? The normal force is not constant, but the force of gravity is constant. Okay. Now remember, you know, this is up, right? the force, the normal force is in the positive direction. Gravitational force is in the negative direction. You've got to be careful with those signs. So that's the impulse from the floor, or the normal force, whatever. So here's the impulse for gravity. All right, so the magnitude is mg. Okay, so it's 0.2 kilograms times, 0.2 times 9.8, right? And it's negative, so it's minus 1.96, minus 1.96 newtons. And we're only talking about the collision. Well, the collision takes 10 milliseconds. How do you know that? Because that's what they gave us, right? They told us that the collision only from the graph, the collision only takes 10 milliseconds. Okay? So this is the graph, right? There's the force, minus 1.96 newtons, and it takes 10 milliseconds. Okay, so we can do it. All right, so J, gravity, it's just a rectangle, right? Length times width. So it's just 10 milliseconds, 10 times 10 minus 3 seconds. And the force is minus 1.96 newtons. And you get minus 0.0196 Newton seconds. Okay, so therefore J total is equal to 2.4 Newton seconds. Newton seconds plus a negative, minus 0.0196 Newton seconds, which is 2.38 Newton seconds. Okay, now, woohoo! Remember, this is our equation for V2y. Okay, so we're there, right? Okay, so therefore, V2y equals J, 2.38 Newton seconds, divided by the mass, 0.2 kilograms, plus V1y, where does that go? Right there. But it's negative, so we minus 6.26 meters per second. And I promise you, you do that, you get 5.64 meters per second. Okay, awesome. All right, so that is, all right, so now we know V2y, right? Okay, so again, look at, first we figured this out from kinematics. We figured this out, impulse momentum, a lot of work, but that's life, Now we want to calculate this. This is kinematics, right? Because this is just gravity, There's no normal force. All right, so now we can finally get Y3. Okay, just, same equation, similar equation, right? Okay, so V3y squared equals V2y squared minus 2g delta y. But remember, it's final minus initial, so it's y3 minus y2. Because all we're doing now is right here, right? Okay, so let's see, but y2 is 0. Oh, that's good. y2 is 0, so we get that. And then we want, just take the square root. And it's going to be positive. It's going up, right? So just plug and chug. Oh, wait a minute. I'm sorry. Well, sorry, that was stupid. We want y3, not v3. Sorry, I know v3 is 0. Okay, I just blew it, but that's okay. Life is still good. This is 0, right? v3y is 0. Okay, so therefore, y3 equals v2y squared over 2g, which is just 5.64 meters per second squared divided by 2g. And you do that, and you get 1.62 meters. Okay, that's the answer. Woohoo! Now, what do you notice? We dropped it from 2 meters and only bounced to 1.62 meters. Does that kind of make sense? Well, isn't some of the energy being wasted at the bottom? Yeah, And so it makes sense that it's not going to rebound to the same height. All right, now let's look at these impulses. The impulse from the floor was 2.4 Newton seconds. The impulse from gravity was minus, let's just say, this is approximately equal to minus 0.02, right? Okay, so how much, is this really important relative to this? Nah. So typically when you have a problem like this, I mean, look. You know, as soon as you see this 480 newtons, you know, and then you look at gravity and it's like minus 2, I mean, this impulse is much, much larger than this impulse. So typically, you just ignore this, all right? That's called the impulse approximation, where you just ignore gravity. But I mean, come on, you can only do it because this was so large, right? If this was not so large, you couldn't ignore this. But I didn't want to ignore it. I just wanted to show you the whole thing. But again, typically, you ignore this if it's super small compared to this, okay? All right, so that's how you do these problems. What do you think? 3 parts, right? You know, wow, kind of a lot. 3 parts: kinematics, impulse momentum, kinematics. And you got to get all 3 parts correct, but that's how it is. Okay. Wow, it didn't take as long as I thought. Well, that's good. Make sure you understand this. This is really important. Okay, now what we want to talk about is, we're still talking about collisions. We want to talk about recoil versus non-recoil. And we're just going to do some approximations, but they're pretty good. So, oops. Okay, so what am I talking about? Recoil, non-recoil. So, can you see this? Okay, so I bought these balls from a physics supply company, and they're called happy and sad balls. And can you see this too down here? All right. Okay, so here's the sad ball. Watch. So we're just going to say that's no recoil. Here's the happy ball. So that's recoil. Okay? All right. We'll come back to that in a minute or so. Okay. So as an example, we're going to talk about rain. Okay? So we're going to talk about rain and something called hail. Okay, let's read let's write the impulse momentum principle. So impulse momentum says that F average delta T equals delta P, correct? That was one way to write the impulse momentum principle. Well, divide both sides by delta T. So you get F equals delta P delta T, okay? So now take the limit as delta T goes to 0, and you get F equals dP dt. I should have vectors over everything, you know. All right? Believe it or not, this is how Newton wrote his second law. He did not write F equals ma, okay? Well, that's okay, because again, I mean, think about it. Okay, this is d dt of momentum, right, of P, which is d dt of mv. Let's say mass is constant. That's the same thing as mass dv dt, which is ma. Woohoo! Okay, but all I'm saying is that when Newton wrote it, he wrote F equals dP dt. Okay, that's really the best way to write it, all right? It really is. Okay, so remember that. So F equals dP dt. All right. Okay, so we're going to talk about 2 situations. So rain and hail. Hope you all know what hail is. So hail, it's like frozen water. So in certain parts of the United States, they get weird weather, and let's say it's raining out, then it gets really cold, and it doesn't snow, it hails. And so you get these frozen balls of ice, which are not pleasant to run in. Okay, so we're going to talk about rain and hail, all right? And again, we're going to make some approximations, you know. Now, yeah, yay, Newton. Okay, so the approximation we're going to make is we're going to say that rain is like the sad ball, okay? And that's not as, come on, this is not completely true, but it's close. So we have the raindrop falling down, and it just splatters, you know? So there's no recoil. Now, is that completely true? No, but it's close enough. All right, we're just talking about the different cases, right? The extreme cases, okay? So the rain, it comes down at some velocity, then it just splatters, so the final velocity is 0. And then, okay, and then the next one is going to be hail, and again, we're just doing the extreme cases, right? The hail, we're going to say, is this. The hail, the speeds are exactly the same, right? So the hail just hits the car and then bounces right back. So the speeds are the same. And again, that's not necessarily true, but it's close. And we're just doing the extreme cases because they're easy. That's really why. Now, I am going to do the rain, and you're going to do the hail. So pay attention so you can do it. Okay, so here's the rain. Because the only way you're going to learn this is by doing it, right? So you got to do it. So the rain. Okay, so here we go. So we want the force of the roof on the rain. Okay, so roof on rain. Okay, because you know the rain comes down and the roof. All right. So again, that's equal to dP or delta P delta T. All right. And delta P is P final, which is mV final, minus P initial, which is mV initial, over delta T. Okay, now, for rain, we're saying it splatters. There's no V final. So that this is 0. So we just get minus mV initial over delta T. Okay? And V initial is this. Sorry. Okay, V initial is this way, right? And a minus sign means it's that way. So this points up. Agree? This points up. Minus mV initial points up. No kidding! I mean, come on. It's the force that the roof exerts on the rain. That points up. Okay, so therefore, the force rain on roof, right, which is the, the negative of that, Newton's third law, is just equal to mV initial over delta T, which points down. Okay, that should not be a big surprise right there, right? The force that the rain exerts on the roof is this way, and that's the magnitude. All right, awesome. Okay, so please, we're going to use this approximation, right? That this speed equals that speed, right? Speed equals speed. So please, so I want you to do the same calculation. There's going to be a little bit of, it's going to be a little bit different though, but similar, Just follow kind of like what I did and use that and see what you come up with. So please pause your video and do the work. Okay, so I'm assuming you've done it. So let's just compare notes, or I'll do it. Okay, so for hail, all right, so I'm just going to copy, force, roof on rain equals delta P over delta T, which is mV final minus mV initial over delta T. Now hold it. Here, we said that mV final was 0, right? So that made it nice. But here, look at, I'm saying that these two speeds or magnitudes are the same, right? So V final, so vector, V final, isn't that equal to vector minus V initial? Well, yeah, right? Same directions, same magnitudes, opposite directions, okay? So I'm going to substitute right there. So I'm going to get my minus sign, minus mV initial minus mv initial over delta t. All right, so that's the difference, right? I have this. This is the difference, right? Okay, well, gee, that equals minus 2 mv initial over delta t. Again, v initial, oops, vector sign, vector sign. Okay, v initial is this way, minus is up, so that's up. No kidding, right? All right, so now what we care about though is the force of the, oh, I shouldn't say rain, it's hail. Hail. So the force that the hail exerts on the roof is opposite of that. It's 2 mv initial over delta t, which is down. So what do you notice? What's the only difference? 2, right? The factor of 2 here. That's the difference. Okay, so if it rebounds, the force is twice as great as if it doesn't rebound. Okay, so no rebound, that's the force that the rain exerts on the roof. With a rebound, with the same magnitudes, the force hail on roof, you get a factor of 2. Okay, factor of 2. So here's some pictures of hail. They're called hailstones. So they can be, look at how big they can be. Big. They can. There's actually been records of these things being the size of a softball. So here's size bigger than a golf ball. Bigger than an apple. So yeah, if you have a car outside during a hailstorm, good luck, right? It's going to smash up your car really, really well. Okay, so bad news. So years ago, I was in Colorado. Let's see, it wasn't Colorado Springs. I don't know, somewhere in Colorado. And it was in late spring. And it was kind of a nice day. Then it got kind of colder, got to get dark, started raining. And then all of a sudden the rain actually turned to hail. So it wasn't snow because it's like chunks of ice. And you just don't want to be outside in that kind of thing, believe me. Okay, so here's a question for you. And you're going to use this, right? A person attempts to knock down a large wooden bowling pin by throwing a ball at it. The person has 2 balls of equal size and mass, one made of rubber and the other of sticky putty. The rubber ball bounces back while the ball of putty sticks to the pin. Which ball is most likely to topple the bowling pin? So pause your video and figure it out. Okay, well, what did we just learn? If there's a rebound, the force is twice as great as no rebound, right? So the rubber ball is going to bounce back, so there's a rebound. The putty doesn't rebound. So obviously the rubber ball is going to have twice the force as the putty, right? It's that factor of 2, right? The factor of 2. Okay, now we're going to see if this is really true. Okay, so again, this is the happy ball and the sad ball, okay? All right, so piece of wood. All right, so this is the sad ball, so there's like no rebound. All right? Now this is the happy ball, so it should exert twice the force that the sad ball did. So I'm not cheating, I'm holding it the same location, I'm not changing anything. Well, you're supposed to fall. Let me do it again. But you can see it was a more force, right? Because it, yeah, all right, okay? So there you go. So factor of 2, just because of the rebound. Okay, that's a, what? Not yet, hold on. Okay, so let's summarize. So here's the impulse momentum theorem. Again, there's different ways of writing it. You can include everything or you just can kind of summarize, but that's impulse momentum, right? It's a force times a time. That's the thing. Force times time. That's what Newton seconds, right? If an object is brought to rest, like the paratrooper question, right? If an object is brought to rest, delta P is blank, whether the object collides with a brick wall, a bale of hay, or whatever. So delta P is what? So pause your video and figure it out. Okay, I hope you agree it's basically the same, right? Because we're saying P final is going to be 0, and the P initials are going to be really super close, right? I mean, if there's a big bale of hay, you know, the velocity or the momentum right before it hits the bale of hay is going to be pretty similar to if it's just hitting the ground, right? Because, I mean, you're not going to have a bale of hay a mile high, right? Okay, so we're saying that the delta P's are the same, okay? Delta P's are the same if an object is brought to rest. All right, therefore, or however, if delta T is short, like if you're hitting the ground, what's going to be true about F? It's going to be large, right? It's going to be large. On the other hand, if delta T is long, like if you're, you know, hitting a pole vault pit or something like that, what's going to be true about F? It's going to be short or small. All right, that's the whole point. And all things being equal, delta P with a rebound equals what? Delta P without? 2, right? Factor of 2, okay? So delta P with a rebound equals twice delta P without a rebound. Therefore, since force is delta P over delta T, if the delta T's are the same, which they were in my little demo, the forces are, right? The force with a rebound equals twice the force without the rebound. All right, that's the impulse momentum theorem in all its glory, right? Okay, yeah, I just said that. Goodbye. All right, stop. Okay, let's quit.